Hello everyone, and welcome to my lecture series on molecular dynamics. And in our previous video lecture, this is what uh, we have done. Let me change my ink color so that you can differentiate. Right, so this is what we have been doing in our previous lecture. The previous lecture began with a simple potential energy surface, and in this potential energy surface, okay, uh, we have plotted over here is time on x-axis, and this is what we call it as the potential energy surface, and on y-axis we have, you can say, positions of atoms or simply coordinates of atom in your protein system, which we have designated as q, and we can also plot the velocities of the atoms that are present in your protein system, and we have indicated by small v, which might be something like this. Okay, so now what our objective was, we'll say, when your protein ligand system or any protein system moves in time in your potential energy surface from point A to point B. We'll say, for example, this is point A and this is point B. Okay, and when your system moves from point A to point B, some delta t time has passed. So at this point A, we know what are the coordinate of our protein ligand system at point T, and at the same point A, we also know what would be the velocity of the atoms that are present in your system at point A, or what we call it as at time T. So our objective, was to predict when this delta T time has passed and your system has now reached point B, where the coordinate would be coordinate at time t plus delta t and velocity at time t plus delta t. Okay, so it was as simple. Okay, we begin at some point where we already knew the positions and velocities of atom in the system, that is q of t and v of t, and our objective was to predict the positions and velocities of the same atoms in the system after this time delta t has passed. That is, we were interested in finding out this term, that what would be the coordinate of our protein ligand at time t plus delta t, what would be the velocity of atoms in our protein ligand system at the time t plus delta t. And to do this, we use the concept of Taylor expansion, or simply Taylor series of expansion, and ended up deriving the two expressions, these two, expression 8 and expression 15. So these expression enabled us to calculate the new position of atoms, that is q of t plus delta t, new position of atoms and new velocities of the atom when our protein ligand system changes its conformation in the time interval of delta t. Okay, so now we know that the two expression that we have derived, expression number 8 and expression number 15, constitute the steps in velocity Verlet algorithm. Okay, now let us again revise what is the significance of these two equations that constitutes the velocity Verlet algorithm before we proceed for further discussion today. So this would be just a kind of revision. So using equation 8, Okay, one is able to find the new coordinates at time t plus delta t. Using this equation 8, one is able to find out new position of atoms at time step t plus delta t. If one knows what would be the coordinate of the previous time step, the velocity of the previous time step, and the energy gradient of the previous time step. So if one knows what were the coordinate of the previous time step, if one knows what were the velocity at the previous time step, and if someone knows what is the energy associated for that structure in the previous time step, one can easily find out what will be the position of the atoms that are involved in your system when your system moves from point A to point B in this potential energy surface, or simply when the atom changes its conformation in your molecular dynamics simulation. So this is equation number 8. In equation number 15, one is able to find out the velocities at the time step t plus delta t, this term. Okay, and how one is able to find out the velocities at the time step t plus delta t? If he know the velocity of the previous time step, okay, if he know the energy gradient of the previous time step and the energy gradient of the current time step. So using these three terms, one can easily find out what might be the velocities of the atoms in your system at the next time step. Okay, so and we said that this is the velocity Verlet algorithm. So now let us discuss how this velocity Verlet algorithm would work. This is what we call it as your Verlet algorithm. Well, let me write these equations first. Okay, so what are we supposed to do now? We are supposed to continue our discussion as to what are the steps that are involved in your velocity Verlet algorithm and how this algorithm is implemented in MD simulations. Okay, so here we have equation number 8. Okay, what do this equation 8 say? It gives you the coordinate of time t plus delta t. If we know the coordinate of previous time step, the velocity of previous time step, and the energy gradient, that is the energy associated with the conformation, that energy associated with the conformation at the previous time step. Okay, so this is equation 8, and similarly we have got equation 15, which gives you an idea as to what would be the velocity of your atoms at time t plus delta t. If we know the velocity of the particles in your system at the previous time step minus delta t by twice m, and the energy gradient, that is the energy associated with the next time step t plus delta t, and the energy associated, or simply the energy gradient of the previous time step. Okay, so this is what is very important. So how our velocity Verlet algorithm work when you perform your MD simulation? So let us draw a simple flowchart that would describe this velocity Verlet algorithm and its functioning. Okay, so let us begin with this start. Every algorithm should begin with start. Okay, and at this starting condition, we'll say for example your protein looks something like this, right? And we'll say for example this is, you know, time t. Okay, at time step t your protein might look like this when the algorithm starts. Next, what we have, so since we have the structure, what we need to do is that we need to calculate the energy gradient or energy associated with this structure, that is this term dv of t by dq of the current time step. This is what we do first. When we start MD simulation, the first thing that we do is that we calculate what is the energy that is associated with the structure that we have started with. Then next, what we do is that we use this equation number 8. What we do is that we use equation 8 for calculating the coordinates of the system at the next time step. Okay, that is positions of atoms at time step when delta t time has passed, when your system has reached this time step q of t plus delta t. Okay, so this is what we do. Okay, so this is where we begin. When we begin the simulation, we begin with calculating the energy that is associated with your protein molecule when you begin it. Okay, and say after time delta t has passed and now your protein has changed its conformation. Okay, and now we say that your protein system is at time step t plus delta t. Okay, so when your system reaches t plus delta t, you already know the energy gradient of the previous time step. Okay, you already know the conformation of the previous time step, and if you know the velocity of the previous time step, you can calculate what would be the position of atoms in your next time step, and you can use this equation 8. Okay, so at the end of this equation 8 we have the new conformation of our protein. Okay, so now since we know the coordinates, or simply the position of atoms in our protein of the next time step, we can calculate the energy gradient of the time step t plus delta t. That is, we are talking about this term now. Now since our system has moved from t to t plus delta t, that is, we have new structure, and since we have new structure, we can now calculate the energy that is associated with this structure. Okay, so we would be calculating this term first. Okay, so once we have this, what we can do is that then we can use this equation number 15. What we are supposed to do is that we are supposed to compute the velocities of the next time step, that is this term v of t plus delta t using equation 15, right? So since we have the new coordinate, we can compute the velocities using this equation. Why? Because we already know what are the velocity of previous time step, what is the energy gradient of the previous time step, and since we have structure of the next time step, we can also compute the energy gradient of that particular configuration or conformation of your protein. And hence, since we have all the terms and expression, you can easily calculate the velocities. Okay, and finally, we ask the question, have we reached the last time step? Because you know we need to do it for multiple times. Okay, now if the answer is yes, that we have reached the last time step, our molecular dynamics program would stop. And if there are still time step remaining, that is if the answer is no, then your program would begin at this step. For the next time step, you would calculate the energy gradient, right? And then calculate equation using equation 8, calculate the coordinate of the new time step. Since you have the coordinate of new time step, you can then calculate the free energy associated with it. Once you have free energy associated with it, you already have the velocities of the previous time, the energy gradient of previous time step and velocity of previous time step. Therefore, using all this data, you can calculate the velocity of next time step, that is vt plus delta t. Again, ask this question, have you reached the last time step, and so on. This algorithm will continue. Okay, so this so-called velocity Verlet is included in special class of algorithm called as the integrator algorithm. This is included, or this is called as the integrator algorithm. And these integrator algorithms are popularly used in MD simulation. They are called as integrator algorithm because they are used to integrate the equations of motion when you perform MD simulation, and you obtain the trajectory this way. So now, in addition to this velocity Verlet algorithm that we have just discussed over here, we have two more additional forms of Verlet algorithm. Okay, and these additional algorithm are called as simple Verlet algorithm. Another variant is leapfrog Verlet algorithm. Okay, so there would be just slight change in the computation, and there are, you can say, two flavors of this velocity Verlet algorithm. We call it as simple Verlet algorithm, and another one is called as leapfrog Verlet algorithm. So this velocity Verlet is the most popularly used form of integrator algorithm in molecular dynamics simulation. Hence, we discussed it here. Okay, so now one you should remember one thing, that all these computation that are shown over here that we have discussed so far, that are done for one time step. You will have to repeat this computation for, say, repetition is to be done for, say, this thousand times if you want to simulate the system for only 1 nanosecond. So when you repeat this step for this thousand or 10 lakh time, then you would be enabled to simulate your protein ligand system for only 1 nanosecond. Okay, so whatever we have discussed, this is a very simple and basic form of algorithm used in MD simulation, and a lot of features are still needed to be discussed over here. Okay, we have not discussed as to how do we control the pressure of your system. We have not discussed temperature control. We have not discussed periodic boundary condition, and so on and so forth. Okay, therefore we will frequently visit this particular slide many times in the course whenever we add a new feature to our MD simulation. Okay, in the subsequent lecture video. So this is, just a very um, crude, you can say, molecular dynamics simulation algorithm, or what we call it as the velocity Verlet algorithm. Okay, we will add a lot of features in our subsequent lectures. Okay, and we would revisit this slide a lot of time. Okay, so this is what we have done, right, in short and conceptually. So what we have done is that, if, please don't mind my graphs, the y-axis never appears to be straight. Okay, consider it as a straight line anyways. So in short and in concept, let me revise what this was all about. Well, let us again draw the potential energy surface of our system. Okay, if this is the potential energy of our system, this is time, and over here we have got the positions and we have got the velocities. Okay, so our objective was to compute the system information at, we'll say, this particular point. Our objective was to compute the velocities and coordinate at time step, you can say, coordinate at time step t plus delta t, and velocity at time step t plus delta t. Okay, and we can compute this information of your protein from the, you can say, previous time step. Okay, when your protein had coordinate q of t and your protein had coordinate velocity v of t. Okay, so the thing is that the coordinate and velocities at the current time step can be computed from the coordinates and velocities of the previous time step. But again, to compute the coordinate and velocities, to compute the position and velocities at this time t, we would again need the information of the same coordinate and velocity at the previous time step, that is q of t minus delta t and velocity of t minus delta t. Okay, so in short, what I mean, and to calculate this, again you might need the coordinate and velocity of its previous time step, right? And in this way you might end up over here, right? In short, what we need is, at the very beginning of the simulation, we need to find out what were the coordinate at the time step t is equal to 0 and velocity at time step t is equal to 0. Okay, so this is what we want to know. In short, what we need at the very beginning of the simulation is the initial coordinates and the initial velocities to initiate your simulation. From these initial velocities and these initial coordinates, the subsequent velocities and coordinates can be calculated all along the course of your trajectory. So in other words, we would require some initial conditions. These are called as initial conditions. We would require this initial condition to begin your MD simulation. Okay. Now you might appreciate that everything eventually boils down to knowing the initial velocities and the initial position of the atoms in your system. If you know the initial positions of the atoms in your protein system and their initial velocities, then you can begin that MD simulation and continue using the integrator algorithm for calculating the subsequent positions and velocity till you reach the end of your simulation. Okay, now let us talk about what are the sources of such initial condition. From where do we obtain the initial condition? Let us talk about the sources of initial conditions. Okay, now we are interested to obtain the initial position and initial coordinate. Initial position, that is what we call it as q at time t is equal to 0, and initial velocities, that is v at time t is equal to 0. Right, we are interested to obtain the initial position and coordinate of atoms in our protein system, and we need to assign the velocities to such individual uh, atoms, right? So the initial coordinate or position of atoms at the initial condition, that is time t is equal to 0, can be obtained from any PDB file or say any homology model structure, or it can be output from molecular docking study if you are interested in simulating a protein ligand complex. Okay, so what are the sources of initial position? It can be a PDB file, it can be a homology model, okay, or it can be docking complex. Okay, so these are usually the initial conditions or initial positions from where you can begin your MD simulation. Okay, now the velocities of the atoms at the initial condition, that is the initial velocities, are randomly assigned from the Maxwell Boltzmann distribution. So initial coordinates can be obtained from PDB or from homology modeling or from docking complexes, and initial velocities that we would need to that we will need to start the simulation is usually randomly distributed or randomly assigned from this Maxwell Boltzmann distribution. Okay, so now let us talk about this Maxwell Boltzmann distribution. What this Maxwell Boltzmann distribution is all about. Okay, so this, what is this Maxwell distribution of velocities in nutshell? Okay, so at the initial stages of learning, I used to wonder when I used to hear such statement like the velocities of atoms at the initial condition are randomly assigned from the Maxwell Boltzmann distribution. I mean, how velocities can be inferred from a graph? It is just a graph, right? How velocities can be assigned to atoms from a graph? Well, let us get these things straight first. Okay, and for that we will need a brief background of the Maxwell Boltzmann kinetic theory. So to understand all these things you would need a background on Boltzmann's kinetic theory. Okay, so this Maxwell Boltzmann kinetic theory will enable us to assign the velocity of particle. Okay, so in brief, this Maxwell Boltzmann kinetic theory, uh, it was based on two main postulates. Okay, it's two main postulates of this Maxwell Boltzmann theory, where that the gases are made up from a very big number of small gaseous particles. Okay, and the second postulate that these guys consider was the gaseous particles are always in motion. So these are the two major postulates based on which this Maxwell Boltzmann build their kinetic theory. Okay, the first postulate being the gases are made up from a very big number of small gaseous particle. There would be huge number of gaseous particle in your system, and such gaseous particle do not remain static and they are always in motion. Okay, so now it is to be noted that the principle proposed in kinetic theory of gases holds equally true in other states as well. Okay, so now coming back to the application of this kinetic theory, in our case we are interested to assign the velocities to individual atoms. Okay, and these atoms are present in very big number in our system. In our system that we were considering, there were some 41912 atoms that were present, if you remember the line number that I have shown you in the text file. Okay, so this is a very big number, right? And the daunting task is to find out velocities for each and every individual atom and assign them to initiate the simulation. Our simple protein ligand system in water contains this much number of atoms. Okay, and if we want to begin the simulation, we will have to figure out what is the velocity of each and every atom, and those atoms are needed to be assigned with those velocities. Then and then you can, you know initiate your simulation. This is where you would begin, right? So now let us assume, uh, this is a very complicated task. Okay, so to find out the uh, velocities of each and every individual atom is a difficult task. Just to give you an idea of complexity of the situation, let us consider an analogy in simpler terms. Okay, so now for our example, let us assume that you own a very fancy cloth shop in a market, right? You own a very good cloth shop in your market. It is very popular jeans shop, and you sell quite fancy jeans to young people. And say for example, it is Diwali time, it is a festive season, and one fine day you wake up and you have to decide on the number of jeans you need to buy for the wholesale from the wholesale, with size of say 30, 32, 34, 36, and so on. Okay, you have a shop, and you need to decide that uh, I need to find out uh, as to how many jeans should I buy from the wholesale, which has got size of 30, 32, 34, 36, and so on. Okay, the objective being whatever customer that will visit your shop in festive season should not leave your shop disappointed that they did not get the jeans that fitted them. Okay, the idea is that every customer should get the size of his or her jeans. Well, now, my friends, it is a very difficult to predict because most of the customer that will approach the shop will be of random size. You don't know as to what will be the size of the incoming customer every time, right? So it is not easy to predict the right size. Then how do we handle such situation? Okay, we are facing the exact same problem in velocity assignment task. Knowing the velocity of individual particle in your protein ligand system is a difficult job, and then how do we approach this solution, right? How exactly do we approach this solution? So there is one method which you can using which you can figure out the solution to this problem. So this method will definitely not give you the 100% accurate results. Why? Because there is randomness involved in your problem. But you will have at least some idea to deal with such tricky situations. Okay, for example, it is very difficult to find out the information of size of individual person that will approach your shop. But what if you have some means by which you can find out how size in the city is distributed? So if you have some means by which you can find out how size is distributed in city. For example, if you know the height of people living in a city, so this can solve your problem. Say in Sensex, every 5 year government reach out to people and collect data like population, male female ratio, income tax, etc. So exactly in the same way, if you have data on height of individual in the city, then you can construct the height distribution, right? So generally the probability distribution of height of individual in any city or area or even in country is like a normal distribution. Okay, in other words, it occurs as a bell-shaped curve. Well, say for example, I would just draw a normal distribution of heights. Okay, so in this say for example, in this height distribution, you can have height in inches on x-axis. Okay, and on y-axis you can plot the number of people. Okay, so your height distribution can look something like this. Okay, for example, in a given figure below, what you see over here is that you have got height on x-axis and the number of people on the y-axis. Okay, good. So we'll say for example, you have got 75, 60 and 70 inches. Okay, so now simply looking at this probability distribution, okay, or you can say just say that this is the height distribution of people in that are living in your city. Okay, so now simply looking at this probability distribution of height, you are now in position to draw few very basic conclusions. Okay, so the very first observation that you can make from such probability distribution is that there will be a very few people. Okay, this graph, the portion of the probability distribution on this side, there will be a very few people in your town that are very short. Who do this area correspond? These are the people that are very short. Okay, and similarly there will be a very few people in your city that are very tall. There is majority of people in the city whose height will lie in between this, say for example 65 to 75 inches, okay, or 65 to 70 inches as such, right? So from such a data of probability distribution, you can figure out that what will be the odds that at any given time, if a customer approaches you and asks you for the jeans of a specific size. Now since you already have this probability distribution by hand, you already know what might be the probability of that size to appear, and based on this data you can estimate the chance of how many people can show up in your shop asking for a specific size of jeans. So we can use such approach to tackle the velocity distribution problem of individual items as well. Okay, so the point is that if you end up working on a problem where you have to deal with a very high number of observation or data points, for example, you are dealing with a system where particle number is very high or number of molecules is very high. In such a case, finding individual particle property becomes a very difficult job. Okay, for example, finding velocities of individual atoms in the system becomes a difficult business. In such cases, if you find a way to figure out the distribution of the property, or simply how your velocity is distributed in the system, then my friends, you can sort out answers to such questions at increasingly higher levels of accuracy. Okay, this is exactly what Maxwell Boltzmann did. So these guys propose two broad concept. Okay, so what Maxwell Boltzmann did is that they proposed two concept. So what was the first concept that they proposed? The very first concept that they propose was that like when you are dealing with higher number in your study, you can use the probability there. Okay, so that was their first principle. Okay, when you are dealing with higher number in your study, you can use probability there to find out the solution. Okay, and what they did next was that they derived a probability distribution function for velocities. This is what they did. Okay, their main contribution was that they stated that when you are dealing with higher number in your study, you can use the probability to find out the solution. And what they did is that they derived a probability distribution function for velocities of particles in your gaseous system. Okay, and this was a very bold and radical concept to propose at that time. Okay, because why? Because at that time scientific society believed on Newtonian mechanics, and the beauty or the strongest point of Newtonian mechanics was the certainty of outcome. You can say that Newtonian mechanics is endowed with certainty of outcome. But in contrast, these guys came up saying that we cannot say certainly, but if you use probability in a large number of molecules, you can end up finding something rather than nothing. Okay, and hence people found it very difficult to digest the proposal of using probability in science at that time. But eventually the scientific community accepted it, and now after more than 150 years we are still using these concepts in our MD simulation. This is the very beauty and the genius of their thinking at that time, right? So these guys proposed a graph showing the distribution of velocities of particles in gaseous system, right? So now let us now talk about the actual Maxwell Boltzmann velocity distribution. Okay, so prior to Maxwell Boltzmann work, scientific society believed that all atoms in a gaseous system will have same velocity, because in system, okay, because particles in system will collide with each other and that will average up the velocities. Maxwell and Boltzmann were the first to propose that it is not the case, and particles present in such a system can acquire velocities ranging from 0 to infinity. And the distribution of such velocities will be like normal distribution. Make note that I said the phrase, it would be like normal distribution. And this is how your graph might look like on, we'll say for example, let me draw this Maxwell Boltzmann distribution. Okay, on x-axis you have molecular speed. Okay, uh, you got speed of the particles in meter per second. Okay, on y-axis we'll say for example you have got number of molecules. Okay, in the original Maxwell Boltzmann distribution there is probability on the y-axis, shown on the y-axis. Okay, there is probability of atoms to have particular velocities. Okay, but for the sake of simplicity and simpler explanation, let us assume we have number of molecules for this instance on y-axis. It will help you digest things quite quickly. Okay, so now we have number of particles or number of molecules on y-axis, and we have speed in meter per second on the x-axis, and your velocity distribution might look something like this. Okay, so we have got velocity. Okay, it begins from 0 and you say that you have got infinity as well. Okay, so the distribution of velocity is in the range from 0 to infinity. Now let us start observing this graph, right? So one thing clearly stand out just at looking this graph is that this graph is not symmetrical graph. And why is that? So if you look at this graph very closely, the minimal velocity value of the particle in the graph is 0. Check out over here. Okay, while the maximum velocity is infinity. So this is the reason why it is not symmetrical like other normal distribution. And this is the reason you have different values for the average velocity and most probable velocity, right? So you have different values for average velocity, and you might have different values for most probable velocity. This is what we mean. Okay, so this graph being not symmetrical, okay, and due to the non-symmetry that is present in your graph, you have different value for average velocity and different value for most probable velocity. If it were symmetrical graph, your average velocity might be the same as the most probable velocity. These two lines would have been the same. Okay, so the second thing you might observe is that the particle velocities keep on increasing till it reaches some point, okay, and then it start to decrease. Okay, the velocity of the particle starts to increase, they reach at some point, and then they eventually start to decrease. What do this behavior mean? Okay, it clearly means that most of your particles in the system will have velocities near or around the most probable velocities. Okay, so this is what I mean. It clearly means that most of the particles that are present in your protein ligand system will have velocities near or around the most probable velocities, somewhere lying around over here. Okay, I hope now you get where I am leading you in this discussion. So there will be a very few particles, we are talking about this, there would be very few particles which will have very low velocity, and there would be very few particles where the particles will have very high velocity and even infinity. Okay, but there are very few such particles, they exist, right? It means that it is possible to have velocity for the particle that might range in between 0 to infinity, right? You may learn one more fact from this simple graph. Okay, well, say if you are interested in finding out a number of particle with some velocity range, okay, then the area under the curve will enable you doing that. Okay, just say for example, if you are interested in finding out as to how many particles are there in my system that have velocity in a range of say 200 meter per second to say 400 meter per second in my Maxwell Boltzmann velocity distribution. Okay, then if you draw a line over here, the whatever area that is present under this particular region will give you, the respective area under curve can give you the particle velocities that are ranging from 200 to 400 meter per second. Okay, so this respective area under curve can give you the particle velocities. See, now you are coming near to assigning the velocities to the particle in your system, right? So this is what in crux in MD simulations, the velocities are randomly assigned to the particles in your system from the particular range in the Maxwell Boltzmann distribution. Okay, you have the structure wherein there are different atoms. In such MD simulation, the velocities are randomly assigned to the particles in your system from a particular range in the Maxwell Boltzmann distribution. Velocity for most of the particles in your protein system will be around the average velocity or most probable velocity. In short, most of your particle will have velocities that will lie in the region around the most probable or average velocity value. So this is where the velocity of maximum number of particles in the system are located, as you can see, right? So using the values from this particular range of velocities, these values are randomly assigned to the particle values that range from, say for example, 200 to 400. Why? Because most number of particles in your protein system will lie around this region. Okay, so now let us continue our discussion with discussing the effect of temperature on the velocity distribution. Okay, we now know that the velocity distribution is a bell-shaped curve, right? This is what we have known, key whatever the velocity distribution is, it is probably going to be a bell-shaped curve, right? And but the problem is the same bell shape can be represented using different curves. Let me show you by drawing these curves, right? So, well, say for example, okay, your curve can be like this, or your curve can be like this. Both of them are bell-shaped curve, right? So the question is, my friend, that for a given system, for a given protein system that we are dealing with, the bell curve shape from which I have to assign my velocity, will it look like this or like this? Okay, on x-axis we have got this velocity in meter per second, and we have got number of particle over here, right? So my question is that if I want to assign the velocities to my particles in my protein system, then should I rely on this bell-shaped curve or should I rely on this bell-shaped curve? Okay, so this fact might lead you to ask the question, what will be the shape of the velocity distribution when I start assigning velocities to the atom in my simulation, right? So Maxwell Boltzmann derived an equation using which you can find out the bell shape of your system. And here is what the equation that they have proposed. Their equation state that there is the probability of velocity can be calculated using this equation. Okay, and in this equation, your k is the Boltzmann constant. V, of course, as usual, correspond to velocity, and your T corresponds to the temperature. Now this is a very scary looking equation. Well, let us not worry about how this equation was derived. We will revisit this equation later on sometime in our course, and we will dissect it there when we learn about how do we perform temperature control in MD simulation. Well, let us let us keep it for that time. For time being, let us focus on what this equation has to offer in context of our velocity distribution, okay, in MD simulation. Well, the very core of this equation is that it offers a relationship between the temperature and the shape of the velocity distribution. It says that the velocity distribution of atom in the system only depends on the temperature. That is what they have derived. It says that the velocity distribution of atoms in any system is only dependent on the temperature of the system. Change the temperature and the shape of the velocity distribution will change, simple as it is. Okay, for example, if we have a same particle system, the graph of velocities will look well, let's say for example, just to explain you this, okay, let me draw a new graph over here. Okay, so we have what we have over is velocity in meter per second, and for example we have particles. Okay, so what I really meant is that let me change the ink color to red. Okay, okay, so we'll say for example this is graph at lower temperature. Okay, and we'll say for example if the temperature is increased, the shape of the same curve would change. Okay, so this is what I mean to say. For example, if we have the same particle system, okay, let us consider that we have our particle system. This is our protein system where our particles are. Okay, for example, if we have the same particle system, the graph of velocities will look like this, the one that I have shown in uh, red color. Okay, the graph of velocities will look like this at the higher temperature, and it will look like this in the lower temperature. Okay, now let us try to understand why is that we have such a difference in graph. Okay, we have got this is for higher temperature. The green graph is for higher temperature and the red graph is for the lower temperature. Okay, and we have got the same system. Okay, so here is what happens. Now let us try to understand why is that we have differences in the shape of your bell curve. Okay, so here is what would happen at the higher temperature. At the higher temperature, the range of the speed of the particles that are present in your system increases. So if you observe the graph at a lower temperature, okay, if you observe the graph at the lower temperature, the red graph I am talking about, okay, you will observe that most of the particles are ranging in between, say, you know 200 to say 400 meter per second. Most of the atoms that are present at lower temperature in the range of 200 to 400 meter per second. Okay, but when you increase the temperature, the range will increase, the range of velocities will increase, and now you can observe that the range of velocities has increased and most particle will be observed in the range of 200 to 600. Okay, by increasing the temperature, from when you go from lower temperature to higher temperature, what happened? The range of the velocities of atoms has increased. Initially it was only this much, most of the particle belong in this much region, but now due to higher temperature the range of velocities has increased from 400 to 600. Okay, so this effect result uh, in an overall broadening of your velocity distribution. Its width increased. You might also note one more fact, that at the lower temperature, the height of the velocity distribution is more as compared to the velocity distribution at higher temperature. Okay, so the reason being the area under curve. Okay, so we have already established that the area under curve will give you the number of molecules in your system, right? Therefore, the number of molecules will remain the same in the system whether it is in high or low temperature. Okay, but at high temperature, you will have more number of molecules with high velocities, right? At higher temperature you have more number of molecules with higher velocities. This much number of molecule has somehow increased. Okay, the distribution thus kind of expands when temperature increases and the height eventually lowers when you increase the temperature. Okay, so that the area under the curve remains the same. Why? Because the number of atoms in your system are not going to change, right? So when you increase the temperature, it would expand, okay, and the height would get decreased. So this is what usually happens in Maxwell Boltzmann distribution. So now let me come to the point as to why I am talking about the effect of temperature on velocity and how it is related to assigning velocities to the particle in my MD simulation. Well, when you simulate a protein system at physiological temperature, well, you know, which is around 310, okay, Kelvin. Okay, you already know the exact temperature at which the velocities are needed to be assigned. The velocity distribution at 310K will remain the same every time you assign the velocities, no matter what your protein system is, right? You will not have to worry about the shape of the velocity distribution when you assign the velocities every time you begin the new simulation. Okay, what I mean to say is that there is a fixed range of velocities available for you to assign to atoms when you do MD simulation. This is what I mean to say. There is a fixed range of velocities that are available for you to assign to atoms when you do MD simulation. It is not that random as we have discussed. Okay, you will use this Maxwell Boltzmann distribution that is developed at a desired temperature. This fact enables you to assign more accurate velocities value to the atom when you initiate the simulation. Okay, and this is how, my friends, you assign the velocities to the atoms at the initial condition to begin your MD simulation at the very first place. So when we initially approached solving the velocity assignment problem, the problem seemed impossible, right? But by application of probability principle in mass particle system, and thanks to very narrow range, or you can say thanks to fixed temperature of the biological system, the problem became manageable, and now you can assign the velocities to the particle with quite certainty. So now you know how we obtained the initial condition. Okay. So if one wants to start a classical MD simulation, then he can guess the initial velocities from the Maxwell Boltzmann distribution. However, one must keep in mind that we have assumed that our protein in water system is under thermal equilibrium. Okay, so it is assumed that your protein and water system that you have generated for molecular dynamics simulation is under thermal equilibrium. Then and then your Maxwell Boltzmann distribution will work properly. Okay, one must keep in mind that we have assumed that our protein in water system is under thermal equilibrium. The system is said to be in thermal equilibrium when the temperature is same in all the regions of the system. Okay, well, say for example, if you have begin solvating your protein molecule in a water box, okay, so when we say that such a protein water system is in thermal equilibrium, when the temperature is constant throughout your box, it should not happen that this much portion of my box has some different temperature and this much portion of my box has got certain different temperature. Okay, then and then your probability distribution would work properly. Why? Because you know that the velocities of particle that we are going to assign in molecular dynamics simulation to begin the simulation, it is completely dependent on the temperature. So it is very important that your system is to be assumed at the thermal equilibrium. Okay, so one more thing. Upon minute observation of the overall molecular dynamics protocol, okay, so let us go back to our protocol. Okay, if you observe this protocol very keenly and if you pay a very keen attention towards the two equations that we are going to solve, that we have derived in the velocity Verlet algorithm, you will notice that in order to compute or in order to complete these two equations, we have to calculate this energy gradient. Okay, this energy gradient or the energy that is associated with your protein's conformation. Okay, we need to know the energy that is associated with the protein system at every time step you will follow your MD simulation protocol. You need to know what is the energy that is associated for my protein in the previous time step, as well as the energy that is associated with my protein in my next time step as well. So without the knowledge of this energy that is associated with your protein, you cannot complete any of the equation of the velocity Verlet algorithm. Okay, that is, we need to know the energy that is associated with our protein system at every time step you move in your molecular dynamics simulation. Right, so we specifically need to know the energy associated with protein at the current time step as well as the previous time step. This is the energy associated with the previous time step, and this would be the energy associated with the current time step. Okay, so now considering this, right, so there are various methods to compute the energy gradient or simply the energy associated with the protein ligand system. Okay, there are various methods for calculating the energy gradient for your protein's conformation, right? So and this energy gradient, you can simply call it as the energy that is associated for each conformation when your molecular dynamics structure will move, right? So now there are various methods for calculating such energy associated with your conformation. Okay, what we have called it as energy gradient. So one of the approach is that if you use these force fields, okay, first approach is to use this force field. Force fields are generally implemented in calculation of such energy gradients. Okay, if force field are used for energy calculation at each time step in MD simulation, we call such an approach as classical MD simulation. Okay, now since these force field uses molecular mechanics, for energy calculation, okay, or you can say since this force field uses a molecular mechanics description for energy calculation, therefore it is also sometimes referred to simply as molecular mechanics simulation. Okay, so therefore we will address the issue of force field and molecular mechanics energy calculation in our next few lecture videos. Okay, so this is, you know, one of the way by which you can calculate the energy gradient to proceed in your velocity Verlet algorithm, and this energy gradient is required in equation 8 as well as equation 15, right? So look at here, we will require energy gradient over here as well as here as well as here, okay, in equation 8 as well as in equation 15. So if you use force field to calculate such energy gradient, then we say that you are performing classical molecular dynamics simulation. And since this force field are dependent, or you can say this force field are molecular mechanics description of energy calculation, therefore we consider such simulation as simulation or molecular mechanics simulation. Okay, and alternatively, okay, we have got an alternative method is that for calculating such energy gradient, well, you can solve Schrodinger's equation. Okay, if the energy gradient is calculated by solving such Schrodinger equation, Schrodinger equation can be briefly given as h of psi is equal to E of psi. Okay, okay, so if you calculate this energy gradient using this Schrodinger's equation, then such a method is called as ab initio molecular dynamics method. Okay, in Schrodinger's equation, h is the Hamiltonian operator and psi is the wave function. Okay, well, let us not go there. Okay, since this is, you know, quantum mechanics description, okay, this is a quantum mechanics description of energy calculation. Therefore, if we use Schrodinger's equation to obtain that energy gradient, we would refer such simulations as QM simulations. Okay, so since this solving Schrodinger equation is a quantum mechanics description for energy calculation, therefore any method that implements Schrodinger's equation for calculating energy gradient is referred to as QM simulations. While there are some hybrid methods that are also developed. Okay, some hybrid methods are also designed that make use of both MM as well as QM, okay, approaches. We call such methods as quantum mechanics or molecular mechanics, or simply QM MM simulations. Okay, the thing is that you might have already came across these terms in a lot of research papers nowadays, and now you exactly know what do they mean. Okay, so by now you might be in position to appreciate the mathematical logic that is implemented behind these MD simulation, and you might now appreciate that how things work in there and what exactly happens behind the scene in the background when you run such simulation. So my friends, this is it for now. So see you guys in our next lecture, right? So we will, in our next lecture we would discuss the issue of force field and how do you calculate such force field. Okay.